Hello, welcome everybody. Here is your mini lecture on section 10-3 on arcs and chords. So I want to begin by just going through a few of the definitions here on your note sheet. I'll start with the arc-chord congruence theorem. This is pretty straightforward. If arcs have equal measure, then the chords are congruent. So we're going to be looking at this circle right here. And it starts by saying if the arcs have equal measure, so I'm going to talk about this arc right here being equal to this arc right here. If those arcs are equal, then these chords are congruent. And that kind of makes a lot of sense if you kind of look at it. And then you could also go backwards. These two things are just backwards of each other. If the chords are equal, then the arcs are equal. Right? And the chords are congruent. Chords can't really be equal. Since that's a shape, chords have to be congruent. Then if we move to the second one stems from a few hard problems in your book. So when we move to the second one, I'm going to keep the same color here I've been using. We'll start with the first one. If the diameter is perpendicular to the chord, a little wording was an issue there, then it bisects the chord. You have to be very careful here. The diameter I'm talking about is this diameter right here, which runs down this whole circle, and it could be turned, of course. Then it bisects a chord. So it could be a radius, too. That's why I drew in the blue radius there, because a radius is basically the extension of a diameter. The chord is down here. So if the diameter is perpendicular, and I did say it is perpendicular right there through the perpendicular symbol, then the chord is bisected, this part and this part right there. So that's kind of important to take notice of. It would be like this part right here and this part right here are the same. Sometimes when I draw a different one, I'll draw like a different one to this chord right here, and I'll go perpendicular to this chord. Some students believe that these two parts are equal. I know that they don't look equal, but if I extended the chord and made it larger, some students do believe that. That is not true. It's only the chord that is equal. So using my specific little lightsaber here, I'm talking about these parts right here. So this part of the chord and this part of the chord. All right. So a lot of that stems from all these different points. If the line is a perpendicular bisector of the chord, then it contains a center. This is just talking all about this one picture here. So if any line in a circle is perpendicular to a chord, like it is right there, then you will touch the center of the circle. Makes a lot of sense. That's kind of backwards of the other one. If a line contains the center of the circle and the midpoint of the chord, then it bisects the central angle. Now what we're talking about there is we're talking about this central angle here that I've extended with these green lines. So basically it bisects this angle. So this angle here and this angle here are going to have equal measure. And if a line bisects a central angle chord, then it's perpendicular. It is the perpendicular bisector. All this stems from this one picture here. So the couple things I just want to mention is that we do have some right triangles here. Kind of notice this right triangle. So when you do a lot of your problems on your worksheets, you're going to be just using the Pythagorean theorem to solve. So it could be that triangle, or it could be this triangle right there. So just look out for the Pythagorean theorem for anything from this section. These examples go really fast. So real world example number 2, use congruent chords to find the arc measure. So in an embroidery hoop, this is a picture of an embroidery hoop, A, B, and C, D are congruent, hence the congruent marks. And the measure of arc AB is 48. The 48's right there. Find the measure of arc CD. Well, this is the arc CD I'm looking for. If this one's 48 because the segments are congruent, the chords are congruent, then this one is also 48 degrees. Okay, makes a lot of sense. That's just a quick little numerical example. And here's an algebraic example. These chords are congruent, so this one goes backwards. I'm sorry, the arcs. The arcs are congruent, so since the arcs are congruent, you also know that these chords are congruent. So if the chords are congruent, we need to find the length of P to Q, so that's this length right here, and we know that it is really x plus 12, so basically we just need to solve for x. So 3x plus 4 equals x plus 12, and solve. Minus x here, cancel, you get 2x plus 4 equals 12. This is a 2, 12. And then you minus 4 to this side, and you get 2x equals 8. And you divide by 2, x equals 4. Now remember, we are trying to find PQ, so PQ is really x plus 12 from the problem, and the x we know is 4, so really it's 4 plus 12, or 16. Pretty simple stuff. Like I said earlier on the note sheet, looking for circles that look like this, that bisect the chord and is perpendicular to the chord. You're going to be looking for Pythagorean theorem on problems that look like this. So do your best to look for those right triangles and solve for Pythagorean theorem. Thanks for listening. Have a good day.